Welcome to Sleepy Science Hub. I'm so glad you've joined me tonight for this gentle journey into one of the ocean's most fascinating mysteries, the extraordinary intelligence that flows through 8 graceful arms and expresses itself in ways that challenge everything we thought we knew about how minds can work. As you settle in, let me know where in the world and at what time you're watching. Whether you're nestled comfortably in your favorite spot as the day winds down, or perhaps finding a quiet moment in the early hours when the world feels still and peaceful, you've discovered the perfect time to explore the remarkable world of octopus intelligence together. Now, get comfortable. Let your body sink into whatever surface supports you. Allow your breathing to slow and deepen, and imagine yourself gently descending into the calm, blue depths of a peaceful ocean. Tonight, we're going to discover how intelligence can flow not just through a single brain, but through 8 independent arms, each capable of its own thoughts and decisions, all working together in harmony to create one of nature's most remarkable minds. Take a slow breath. Feel yourself floating weightlessly in this underwater realm. And let's begin. Imagine yourself drifting slowly through crystal clear water, suspended in the gentle embrace of a calm ocean where shafts of golden sunlight filter down from above, creating dancing patterns of light and shadow on the sandy seafloor below. The water around you is the perfect temperature, neither too warm nor too cool, supporting your body with the effortless buoyancy that makes every movement feel graceful and deliberate. As you float here in this peaceful underwater realm, your breathing naturally slows to match the rhythm of the gentle currents that sway the sea grasses and kelp fronds in their eternal, meditative dance. The seafloor beneath you is not barren sand, but rather a diverse landscape that seems almost like an underwater garden, dotted with colorful coral formations, clusters of shells in countless shapes and sizes, and rocky outcroppings that provide shelter and hiding places for the countless creatures that call this peaceful realm home. Small fish drift past you in schools that move with the synchronized precision of living clouds, their silver scales catching the filtered sunlight in brief, sparkling flashes that create momentary constellations in the blue-green water around you. As your eyes adjust to the gentle dimness of this underwater world, you begin to notice details that weren't immediately apparent. What you first took to be a cluster of rocks near a coral formation reveals subtle signs of something more intriguing. There's a slight irregularity in the texture, a barely perceptible movement that suggests life rather than the simple stillness of stone. The surface seems to shimmer slightly, as if the rock itself is breathing, and you notice what appears to be a small opening, perfectly round, that might be watching you with the patient curiosity of an intelligent observer. This is your first glimpse into the remarkable world of the octopus, though you might not realize it yet. These masters of disguise are so skilled at blending with their surroundings that they can become virtually invisible, their bodies taking on not just the color, but also the texture and even the apparent rigidity of the rocks, corals, and sand around them. What seems like a simple rocky outcrop might actually be home to one of the ocean's most sophisticated minds, an intelligence so different from our own that it challenges our basic assumptions about what it means to think and to be aware. The octopus observing you from its hidden position demonstrates intelligence in ways that are both immediately visible and subtly complex. Its large eyes, proportionally among the most sophisticated in the animal kingdom, track your movements with the kind of focused attention that suggests not just awareness but active evaluation. Behind those eyes lies a brain that processes visual information with remarkable speed and precision. But more fascinating still is the fact that much of the octopus's intelligence doesn't reside in its central brain at all, but is distributed throughout its 8 arms, each of which contains its own neural networks capable of independent thought and decision-making. As you watch, maintaining the slow, non-threatening movements that allow for peaceful observation in the underwater world, you might notice the slightest shift in the creature's position. One arm extends slightly, moving with such fluid grace that it seems less like the movement of a limb and more like the flowing of water itself. This arm explores the space around it with the gentle curiosity of a hand reading Braille, its surface covered with thousands of sensitive receptors that can taste, smell, and feel textures with an acuity that far exceeds human capabilities. The arm moves independently of the others, making its own decisions about where to explore and what to investigate, while somehow remaining perfectly coordinated with the overall behavior of the animal. This represents one of the most remarkable aspects of octopus intelligence: the way individual arms can act autonomously while contributing to the collective awareness and decision-making of the whole creature. Each arm is, in a very real sense, capable of its own thoughts, its own learning, and its own memory, yet all 8 work together in harmony to create a form of distributed intelligence unlike anything else we know. The octopus's skin tells its own story of intelligence in action. As you observe, you might notice subtle changes in color and texture rippling across its surface like thoughts made visible. This isn't simply camouflage, though the creature's ability to blend perfectly with its surroundings is certainly remarkable. The changing patterns on its skin represent a form of external thinking, a way of processing information and communicating that extends the creature's cognitive abilities beyond the boundaries of its brain and nervous system into the very surface of its body. Each color change, each shift in texture, represents the firing of thousands of specialized cells called chromatophores, each one controlled by the octopus's nervous system with the precision of pixels in a high-resolution display. But unlike a simple display screen, the octopus's skin is interactive, both expressing the creature's internal states and gathering information from its environment. The skin can taste the water around it, detect chemical signals from other creatures, and even sense changes in light and shadow that might indicate the approach of something worth investigating or avoiding. As you continue your peaceful observation, you begin to understand that you're not simply watching an animal going about its daily routine, but rather witnessing a form of intelligence that operates according to principles fundamentally different from our own. Where human intelligence is centralized, flowing from a single brain through a hierarchical nervous system, octopus intelligence is distributed, flowing through multiple independent processing centers that somehow coordinate to create unified, purposeful behavior. The octopus moves with the fluid grace of a creature perfectly adapted to its three-dimensional aquatic environment. Unlike land animals that must contend with gravity and the need to maintain contact with the surface for support, the octopus moves freely through all dimensions of its watery world, able to approach any object or investigate any space from any angle. This freedom of movement seems to have contributed to a form of spatial intelligence that allows the creature to navigate complex three-dimensional mazes, remember the locations of dozens of potential hiding spots, and plan routes through its territory with the skill of an experienced navigator. The arms work in constantly shifting combinations to propel the octopus through the water, some providing thrust while others steer, some exploring ahead while others trail behind, gathering information about the route traveled. This constant coordination between independent limbs requires a form of distributed awareness that can monitor and coordinate multiple simultaneous activities while maintaining overall coherence of purpose. It's like watching a jazz ensemble where each musician is improvising independently while somehow maintaining perfect harmony with the whole. When the octopus encounters an object of interest, perhaps a shell that might make a suitable addition to its collection, or a small cave that could serve as a temporary shelter, you can observe problem-solving intelligence in action. The creature doesn't simply react instinctively, but rather appears to evaluate the situation, consider options, and make decisions based on past experience and current needs. An arm extends to investigate, gathering information through touch, taste, and smell, while the eyes continue to monitor the broader environment for potential threats or opportunities. The octopus's approach to exploration reveals intelligence that is both methodical and creative. It will systematically investigate every aspect of an object or space, using different arms to examine different features simultaneously, while integrating all this sensory information into a comprehensive understanding of what it has encountered. This multi-channel processing allows the octopus to gather far more information in a shorter time than would be possible with a single investigative appendage. demonstrating how distributed intelligence can be more efficient than centralized processing for certain types of tasks. The social dimension of octopus intelligence, while more subtle than the obvious problem-solving abilities, reveals itself in the creature's awareness of your presence and its evaluation of whether you represent a threat, an opportunity, or simply a neutral presence to be monitored. The octopus's behavior adjusts based on your movements and proximity, demonstrating a sophisticated understanding of the intentions and capabilities of other beings. This social intelligence operates through the same distributed processing that characterizes all aspects of octopus cognition, with multiple arms gathering information while the eyes monitor and the skin processes chemical and tactile signals. Memory plays a crucial role in octopus intelligence, and you might observe behaviors that suggest the creature is drawing on past experiences to inform current decisions. The octopus might avoid certain areas where it previously encountered danger or return to locations where it found food or suitable shelter materials. This spatial memory appears to be remarkably detailed and persistent, allowing the creature to maintain mental maps of large territories and remember the specific characteristics of numerous locations over extended periods. The octopus's relationship with its environment reveals intelligence that extends beyond simple adaptation to active modification and manipulation. These creatures are known to collect objects that serve various purposes: shells for armor, rocks for construction, tools for food extraction, demonstrating an understanding of how environmental resources can be repurposed to serve current needs. This behavior suggests not just intelligence, but creativity, the ability to see potential uses for objects beyond their obvious functions. As you float peacefully in this underwater realm, observing these demonstrations of distributed intelligence in action, you begin to appreciate the remarkable evolutionary achievement that the octopus represents. Here is a creature that has developed sophisticated cognitive abilities through a completely different neural architecture than our own, proving that intelligence is not limited to the centralized, hierarchical systems that characterize vertebrate brains, but can emerge through distributed, networked approaches that may in some ways be more flexible and resilient than our own cognitive strategies. The octopus's intelligence operates in real time, with sensory information, decision-making, and motor responses all flowing seamlessly through the distributed network of brain and arm-based neural clusters. There's no apparent delay between perception and response, no bottleneck where information must be processed through a central authority before action can be taken. This real-time processing gives octopus behavior a fluid, responsive quality that allows the creature to adapt instantly to changing circumstances while maintaining the complex, long-term planning capabilities that characterize sophisticated intelligence. The peaceful observation of octopus intelligence in its natural environment provides insights not just into how these remarkable creatures think, but into the fundamental nature of intelligence itself. By watching an octopus navigate its world, solve problems, interact with its environment, and demonstrate awareness and intention, we begin to understand that intelligence is not a single phenomenon, but rather a family of related capabilities that can emerge through many different neural architectures and express themselves in countless different ways. As you drift in the gentle currents of this underwater garden, surrounded by the quiet beauty of the ocean depths and the subtle demonstrations of distributed intelligence flowing through 8 graceful arms, you're witnessing one of evolution's most remarkable experiments in cognitive architecture. The octopus represents proof that intelligence is far more flexible, creative, and diverse than we once imagined, opening our minds to new possibilities for understanding not just how other creatures think, but how intelligence itself can emerge, adapt, and flourish in the endless creativity of the natural world. In this underwater realm, floating weightlessly among the gentle swaying of kelp fronds and the soft filtering of sunlight through the crystal-clear water, you begin to notice something extraordinary happening on the surface of the octopus's body. What you initially perceived as simple camouflage reveals itself to be something far more sophisticated. A living canvas where thoughts become visible, with a boundary between mind and body dissolves into flowing patterns of color and texture that represent one of nature's most remarkable achievements in cognitive expression. The octopus's skin is not merely a protective covering or a passive display system, but rather an extension of its nervous system, so intimate and sophisticated that it functions as an external brain, processing information, expressing internal states, and communicating with the environment in ways that challenge our basic understanding of where the mind ends and the body begins. Every square inch of this living surface contains thousands of specialized cells called chromatophores, each one connected directly to the octopus's nervous system and capable of changing color and transparency with the speed of thought itself. Imagine your own thoughts made visible, flowing across your skin in patterns of light and shadow, color and texture, expressing not just what you're thinking, but how you're feeling, what you're remembering, and what you're planning to do next. This is the reality of octopus cognition, where the skin serves as both input device and output display, gathering information from the environment while simultaneously expressing the complex internal processes of a remarkably sophisticated mind. The octopus thinks, quite literally, with its entire body surface, creating a form of embodied cognition that extends far beyond the boundaries of its central brain. As you watch, mesmerized by the slow, hypnotic changes rippling across the creature's surface, you witness what can only be described as visible thinking. Waves of color flow from the head toward the arms, like neural signals made manifest, carrying information and coordination signals throughout the distributed network of the octopus's extended nervous system. These chromatic waves don't move randomly, but follow specific pathways and patterns that suggest complex information processing occurring in real time across the creature's entire body surface. The chromatophores themselves represent a marvel of biological engineering that operates on principles both elegant and complex. Each cell contains tiny sacs filled with different colored pigments, reds, yellows, browns, and blacks, surrounded by radiating muscle fibers that can contract and expand the pigment sacs with extraordinary precision. When the muscles contract, the pigment spreads out, making that color visible. When they relax, the pigment contracts into a tiny, invisible dot. The coordination of millions of these cells creates the flowing patterns of expression that make the octopus's skin a living work of art. But the chromatophores are only one layer of this sophisticated display system. Beneath them lie iridophores, cells containing reflective platelets that can be oriented to reflect different wavelengths of light, creating metallic silvers, blues, and greens that shimmer and shift like living mercury. Deeper still are leucophores, cells that can scatter light to create whites and lighter tones, providing the full spectrum of color and brightness that makes the octopus's chromatic displays so remarkably diverse and expressive. The speed at which these changes occur is breathtaking. Patterns can sweep across the octopus's body in fractions of a second, faster than the human eye can fully process. This rapid-fire communication system allows the octopus to express complex information almost instantaneously, whether it's blending perfectly with a coral reef, warning off a potential threat, or communicating subtle intentions to another octopus. The skin becomes a high-bandwidth communication channel that operates in parallel with the creature's other cognitive processes, adding layers of meaning and nuance to every behavior. The thinking skin serves multiple cognitive functions simultaneously, demonstrating a level of parallel processing that human technology is only beginning to approximate. While some chromatophores are busy creating camouflage patterns that match the current environment, others might be displaying emotional states or social signals, while still others are processing sensory information from the surrounding water. This multitasking capability represents a fundamental difference between octopus cognition and our own more sequential, centralized approach to information processing. Temperature and texture changes add yet another dimension to the octopus's thinking skin. Specialized muscles can create raised papillae that transform the smooth surface into a landscape of bumps, ridges, and protrusions that perfectly mimic the texture of coral, rocks, or algae. These textural changes occur with the same speed and precision as the color changes, creating three-dimensional camouflage that can fool even the most observant predator. More remarkably, these texture changes appear to be coordinated with specific thought processes, as if different cognitive states are associated with different surface topographies. The octopus's ability to taste and smell through its skin adds layers of sensory intelligence to this remarkable system. Chemical receptors distributed across the body surface can detect dissolved substances in the water, providing detailed information about nearby creatures, food sources, and environmental conditions. This chemical sensing ability transforms the entire skin surface into a distributed nose and tongue, gathering chemical information that is immediately processed and integrated with visual and tactile data to create a comprehensive understanding of the surrounding environment. Touch receptors embedded throughout the skin provide another stream of sensory input that flows directly into the octopus's distributed intelligence network. These receptors can detect water movement, pressure changes, and physical contact with extraordinary sensitivity, allowing the octopus to sense the approach of other creatures, navigate in murky water, and manipulate objects with incredible precision. The skin becomes a full-body sensing array that provides far more detailed environmental information than any single sensory organ could deliver. The social communication aspects of the thinking skin reveal layers of complexity that researchers are only beginning to understand. Different patterns and color combinations appear to convey specific meanings, creating a visual language that operates alongside the octopus's other communication methods. Rapid flickering patterns might indicate excitement or agitation, while slow, flowing waves of color could represent calm evaluation or peaceful intentions. The subtlety and sophistication of these visual communications suggest that octopuses possess a rich emotional life that is expressed through their remarkable chromatic displays. Learning and memory are literally written on the octopus's skin, as the creature's past experiences influence the patterns and responses that emerge during different situations. An octopus that has learned to associate certain colors or textures with safety or danger will incorporate these learned associations into its chromatic responses, creating a living record of accumulated knowledge that is expressed through skin patterns. This embodied memory system allows the octopus to respond to new situations based not just on immediate sensory input, but on the accumulated wisdom encoded in its chromatic vocabulary. The dreamlike quality of the octopus's skin patterns creates an almost hypnotic effect as you observe the flowing changes in color and texture. Geometric patterns emerge and dissolve like visual music, creating rhythms and harmonies that seem to follow their own internal logic. Bands of color sweep across the surface like brush strokes on a living canvas, while intricate designs appear and disappear with the fluid grace of thoughts materializing and fading in consciousness. These patterns possess an aesthetic beauty that suggests the octopus's thinking processes have an inherent artistry that emerges naturally from the sophisticated interplay of neural activity and chromatic expression. The territorial and navigational functions of the thinking skin become apparent as you observe how the octopus's patterns change in response to different locations and environmental features. Specific chromatic signatures might be associated with particular territories or landmarks, creating a visual mapping system that helps the creature navigate its complex three-dimensional environment. The skin becomes a living GPS system that displays location-specific information while simultaneously processing sensory data about current surroundings. Problem-solving behaviors are accompanied by characteristic skin patterns that seem to reflect the cognitive processes occurring within the octopus's distributed intelligence network. When the creature encounters a challenging situation, perhaps a tightly closed shell containing a potential meal, or a complex maze of coral formations to navigate, specific patterns emerge that appear to correspond to different aspects of the problem-solving process. Exploratory patterns might appear during initial investigation, while more focused, intense coloration could indicate concentrated cognitive effort. The octopus's skin also serves as a mood ring of extraordinary sophistication, expressing emotional states with a clarity and nuance that makes the creature's feelings immediately visible to any observer who knows how to read the chromatic language. Stress, curiosity, aggression, fear, contentment, and excitement all have their characteristic color patterns and textural signatures, creating an emotional transparency that is both beautiful and scientifically fascinating. This external display of internal states provides researchers with unprecedented insight into the emotional lives of these remarkable creatures. The healing and regenerative properties of the thinking skin add another dimension to its cognitive functions. When injured, the octopus can rapidly reorganize its chromatic displays to compensate for damaged areas, rerouting visual communications through undamaged regions while the healing process takes place. This adaptability demonstrates that the thinking skin is not a fixed system, but rather a flexible, self-repairing network that can maintain its cognitive functions even when portions are temporarily compromised. Environmental adaptation through the thinking skin occurs continuously as the octopus moves through different habitats and encounters varying conditions. The chromatic system automatically adjusts its baseline patterns to match new environments, while learning algorithms encoded in the neural networks refine the matching process based on feedback about the effectiveness of different camouflage strategies. This real-time adaptation represents a form of environmental intelligence that allows the octopus to maintain optimal concealment regardless of how its surroundings change. The social learning aspects of chromatic communication become apparent when observing multiple octopuses in close proximity. Young octopuses appear to learn chromatic vocabulary by observing the patterns displayed by adults, gradually developing their own sophisticated visual communication abilities through a process that resembles language acquisition in human children. This cultural transmission of chromatic knowledge suggests that octopus communities may develop regional dialects of visual communication, with different populations expressing similar concepts through slightly different color patterns and sequences. The energy efficiency of the thinking skin represents another remarkable aspect of this biological system. Despite the incredible complexity and speed of the chromatic displays, the metabolic cost of operating the system appears to be remarkably low, allowing the octopus to maintain continuous cognitive processing through its skin without depleting its energy reserves. This efficiency suggests that the thinking skin represents an optimal solution to the challenge of distributed information processing, providing maximum cognitive capability with minimal energy expenditure. The artistic dimension of octopus chromatic displays becomes increasingly apparent as you observe the subtle aesthetic choices that seem to influence pattern selection. Beyond the functional requirements of camouflage and communication, the octopus appears to exercise a form of creative expression in its skin patterns, choosing from multiple equally effective options based on what could only be described as aesthetic preferences. This artistic sensibility suggests that the octopus's thinking skin serves not just practical cognitive functions, but also provides a medium for creative self-expression that adds richness and individuality to each creature's behavioral repertoire. The meditation-inducing quality of observing the octopus's thinking skin creates a deeply peaceful and contemplative state in the observer. The flowing patterns of color and texture seem to synchronize with deeper rhythms of consciousness, creating a visual mantra that draws the mind into increasingly relaxed and receptive states. As you float in the gentle embrace of the underwater environment, watching thoughts made visible flow across this living canvas, you begin to understand that you're witnessing not just an exotic biological phenomenon, but a fundamental demonstration of how intelligence can express itself through beauty, grace, and the seamless integration of mind and body into a unified system of extraordinary sophistication and elegance. The thinking skin of the octopus represents one of evolution's most remarkable achievements in cognitive innovation, proving that intelligence need not be hidden away inside a protective skull, but can flow freely across the surface of a living being, expressing itself through patterns of beauty that make thought visible and transform the boundary between mind and body into a permeable interface where consciousness and physical form dance together in eternal, ever-changing harmony. As you continue floating in this tranquil underwater realm, your attention is drawn to the most extraordinary aspect of octopus intelligence: the gentle, purposeful movements of 8 arms that operate with a degree of independence that challenges everything we thought we knew about how minds organize and coordinate complex behavior. Each arm moves with its own rhythm and intention, exploring different aspects of the environment simultaneously, yet somehow maintaining perfect harmony with the overall goals and awareness of the creature as a whole. This is not simply a matter of one brain controlling 8 limbs, but rather 8 semi-independent minds working in collaborative harmony to create a form of distributed intelligence that represents one of evolution's most remarkable experiments in cognitive architecture. Imagine, for a moment, if each of your arms possessed its own capacity for thought, its own memory, its own ability to learn and make decisions. Picture how your left hand might be exploring one object while your right hand investigates something completely different, each gathering information and making autonomous decisions about how to proceed, yet somehow coordinating their activities with your overall intentions and awareness. This is the daily reality of octopus cognition, where each arm contains approximately 40 million neurons, more than some entire vertebrate brains, organized into sophisticated neural networks that can process sensory information, control movement, and even learn from experience without direct oversight from the central brain. The neural architecture of each arm resembles a self-contained information processing system that remains in constant communication with both the central brain and the other arms through a complex network of nerve pathways. This distributed processing allows the octopus to gather and analyze information from 8 different sources simultaneously, creating a bandwidth of environmental awareness that far exceeds what any centralized intelligence system could achieve. Each arm can taste, smell, feel texture, detect chemical gradients, and assess the physical properties of objects independently, while sharing this information with the rest of the system through sophisticated neural integration protocols. As you observe the octopus moving through its underwater garden, you witness this distributed intelligence in action as arms explore different crevices in a coral formation simultaneously. One arm investigates a small cave that might contain food, its sensitive suckers tasting the water for chemical traces of potential prey, while another arm examines a collection of shells that could serve as construction materials for the octopus's den. A third arm maintains contact with the substrate, ensuring stability and providing continuous tactile feedback about the creature's position, while a fourth arm reaches upward, monitoring the water column for any signs of approaching threats or opportunities. The sensory capabilities of each arm represent a marvel of biological engineering that operates on principles of distributed intelligence gathering. The hundreds of suckers that line each arm are not simple suction devices, but rather sophisticated sensory organs that combine the functions of fingers, tongue, and nose into integrated units capable of extraordinary discrimination and sensitivity. Each sucker contains thousands of chemoreceptors that can detect and analyze dissolved chemicals with sensitivity that exceeds the most sophisticated laboratory instruments, allowing the arm to literally taste its way through the environment while simultaneously gathering tactile and spatial information. The movement patterns of individual arms reveal cognitive processes that operate according to principles of autonomous decision-making within a collaborative framework. When an arm encounters an object of interest, it can choose from a vast repertoire of investigation strategies without waiting for instructions from the central brain. The arm might begin with gentle exploration using the tips of its suckers to assess texture and chemical composition, then progress to more intensive investigation if the initial results prove promising, or move on to examine other objects if the first assessment suggests little value or potential danger. This autonomous decision-making capability extends to learning and memory, with each arm capable of acquiring new skills and retaining information about successful strategies and techniques. An arm that learns an effective method for extracting food from a particular type of shell can remember and apply this technique independently, even when the central brain is focused on other tasks. This distributed learning system allows the octopus to develop multiple specialized skill sets simultaneously, with different arms becoming expert at different types of manipulation and investigation. The coordination between arms reveals communication protocols that operate below the level of conscious awareness, creating seamless collaboration between multiple independent processing systems. When the octopus encounters a complex problem that requires the coordinated action of several arms, the neural communication between limbs allows for rapid coordination and task distribution without apparent central oversight. Arms can pass objects between them, coordinate their movements to achieve common goals, and even compensate for each other's limitations in a demonstration of cooperative intelligence that emerges from the distributed processing capabilities of the system. The spatial intelligence demonstrated by octopus arms operates in 3 dimensions with a sophistication that reflects their adaptation to the complex underwater environment. Each arm must navigate through spaces that change constantly as currents move vegetation, as other creatures create new obstacles, and as the octopus itself moves through its territory. The spatial processing required for this navigation appears to be distributed among the arms themselves, with each limb maintaining its own spatial map of immediately surrounding areas while contributing to the overall spatial awareness of the creature. Tool use behaviors reveal how distributed intelligence can emerge through the coordination of multiple independent processing systems, each contributing its own capabilities to achieve goals that no single arm could accomplish alone. When an octopus uses a rock to crack open a shell, multiple arms coordinate their activities in sophisticated ways. Some arms position and stabilize the shell, others manipulate the rock tool, while still others monitor the process and adjust the technique based on feedback about effectiveness. This coordination happens fluidly and naturally, suggesting that the distributed intelligence system has evolved sophisticated protocols for multi-arm collaboration. The memory systems of individual arms demonstrate remarkable capacity for storing and retrieving information about environmental features, successful techniques, and spatial relationships. Each arm appears to maintain its own memory banks about the objects it has encountered, the strategies that have proven effective in different situations, and the spatial layout of frequently visited areas. This distributed memory system allows the octopus to maintain detailed knowledge about far more environmental features than could be stored in any centralized memory system, while ensuring that relevant information is immediately available to the arm that needs it. Problem-solving behaviors showcase how distributed intelligence can approach challenges from multiple angles simultaneously, with different arms trying different strategies in parallel until an effective solution emerges. When confronted with a puzzle box containing food, an octopus might have one arm probing for mechanical weak points, while another searches for chemical traces that might indicate hidden openings, and a third arm experiments with different manipulation techniques. This parallel processing approach allows for rapid problem-solving that combines multiple investigative strategies simultaneously. The learning capabilities of individual arms extend beyond simple stimulus response conditioning to include sophisticated pattern recognition and strategy adaptation. Arms can learn to recognize subtle environmental cues that indicate the presence of food, danger, or opportunity, and can modify their investigation techniques based on experience with similar situations. This learning occurs independently in each arm while being integrated into the overall behavioral repertoire of the creature, creating a system where experience accumulates across multiple parallel processing channels. The communication between arms occurs through both neural pathways and behavioral cues, creating a rich information exchange that coordinates the activities of the distributed intelligence system. When one arm discovers something significant, it can signal other arms through direct neural communication or through behavioral changes that other arms can detect and interpret. This creates opportunities for rapid information sharing that allows the entire system to benefit from discoveries made by any individual component. The emotional and motivational states that influence arm behavior demonstrate how distributed intelligence systems can maintain coherent goals and intentions while allowing for individual variation in approach and technique. Each arm appears to be influenced by the overall emotional state of the creature, while retaining some degree of autonomy in how it responds to these internal states. This creates behavior that is both unified in purpose and varied in execution, allowing for adaptive flexibility while maintaining coherent goal-directed activity. The regenerative capabilities of octopus arms reveal how distributed intelligence systems can maintain functionality even when components are lost or damaged. When an arm is lost, the remaining arms can compensate for its absence while the damaged limb regenerates, and a new arm gradually develops its own neural networks and processing capabilities. This regenerative intelligence suggests that the distributed processing system includes mechanisms for dynamic reconfiguration and adaptation that maintain system functionality despite significant component loss. The social intelligence demonstrated through arm behaviors reveals how distributed processing systems can engage in complex social interactions that require coordination between multiple independent cognitive systems. When interacting with other octopuses, arms can engage in elaborate communication displays that involve coordinated movements, color changes, and spatial positioning that convey complex social information. These interactions require real-time coordination between multiple arms while maintaining awareness of the social context and the responses of other individuals. The hunting strategies employed by octopus arms demonstrate how distributed intelligence can coordinate complex, multi-step behaviors that require precise timing and spatial coordination. When capturing prey, different arms take on specialized roles. Some arms herd and position the prey. Others deliver the capture stroke, while still others prepare to transfer the captured food to the mouth. This role specialization happens fluidly and adaptively, with arms taking on different roles based on the specific hunting situation and the behavior of the prey. The exploratory behaviors of individual arms reveal curiosity and investigation patterns that suggest each limb possesses its own drive to gather information and understand its environment. Arms will explore novel objects and environments with apparent intrinsic motivation, even when there's no immediate survival benefit to such exploration. This distributed curiosity creates a system where learning and environmental awareness accumulate continuously across multiple parallel channels, ensuring that the octopus maintains comprehensive knowledge about its territory and the resources it contains. The construction and manipulation behaviors demonstrated by octopus arms show how distributed intelligence can engage in complex engineering projects that require planning, coordination, and execution across multiple independent processing systems. When building dens or arranging defensive barriers, arms work together in sophisticated construction projects that demonstrate understanding of structural principles and aesthetic preferences. Each arm contributes its own capabilities to the construction process while maintaining awareness of the overall design goals and structural requirements. As you float peacefully in this underwater realm, observing the graceful coordination of 8 independent minds working in perfect harmony, you begin to understand that you're witnessing a form of intelligence that challenges our basic assumptions about how consciousness and awareness can be organized. The octopus demonstrates that effective intelligence doesn't require centralized control or hierarchical organization, but can emerge through the collaboration of multiple independent processing systems that maintain their autonomy while contributing to collective goals and awareness. The 8 independent minds of the octopus represent a profound lesson in the flexibility and creativity of intelligence itself, showing how evolution can discover radically different solutions to the challenges of survival and environmental adaptation. In the gentle, purposeful movements of 8 arms, each possessed of its own capacity for thought and decision-making, we glimpse possibilities for intelligence that extend far beyond our own cognitive architecture, opening our minds to new understanding of how awareness and intention can manifest in the endless creativity of living systems. As you continue your peaceful observation in this underwater sanctuary, floating effortlessly among the gentle currents and dancing patterns of filtered sunlight, you witness one of nature's most sophisticated demonstrations of creative intelligence as the octopus encounters challenges that require not just instinctive responses, but genuine problem-solving abilities that rival those of the most intelligent vertebrates. The creature's approach to novel situations reveals cognitive processes that combine logic and creativity, memory and innovation, patience and determination in ways that demonstrate how intelligence can manifest through biological architectures completely different from our own. Watching an octopus solve problems is like observing thought made visible, as the creature's entire body becomes involved in the cognitive process. The skin displays shifting patterns that seem to reflect internal mental states. Arms explore different aspects of the challenge simultaneously, and the eyes maintain constant surveillance of the broader environment while the mind works through the logical steps necessary to achieve its goals. This whole-body engagement in cognitive activity creates a form of embodied intelligence, where thinking becomes a physical process that engages every aspect of the creature's being. The octopus's first approach to any new challenge typically involves systematic investigation, with different arms assigned to gather different types of information about the problem at hand. If the creature encounters a sealed container that might contain food, one arm will explore the container's exterior surface, mapping its shape and texture while searching for potential openings or weak points. Another arm might probe the surrounding area, ensuring that the investigation can proceed safely without exposing the octopus to danger. A third arm maintains contact with a secure retreat route, while others stand ready to assist once the initial assessment is complete. This methodical approach to problem-solving demonstrates planning capabilities that extend well beyond simple trial-and-error learning. The octopus appears to form mental models of problems before attempting solutions, evaluating different possible approaches and selecting strategies based on past experience and current environmental conditions. This cognitive process involves the integration of information from multiple sources: visual assessment, tactile exploration, chemical analysis, and memory of similar situations, synthesized into coherent understanding that guides strategic decision-making. Memory plays a crucial role in octopus problem-solving, as the creature draws upon a vast repository of past experiences to inform current decisions. The distributed memory system, spread across the central brain and the neural networks in each arm, allows for rapid retrieval of relevant information about similar challenges encountered in the past. This might include memories of successful techniques for opening different types of shells, strategies for navigating complex three-dimensional mazes, or solutions to mechanical puzzles that required multiple steps to complete. The learning process itself reveals remarkable flexibility and creativity in how the octopus acquires new problem-solving skills. Unlike simple conditioning that associates specific stimuli with specific responses, octopus learning involves the development of general principles and strategies that can be adapted to new situations. When an octopus learns to open one type of container, it doesn't simply memorize a fixed sequence of movements, but rather develops an understanding of mechanical principles that can be applied to different containers with different closure mechanisms. Innovation emerges naturally from the octopus's problem-solving process, as the creature combines known techniques in novel ways to address unprecedented challenges. When faced with a problem that doesn't match any previous experience exactly, the octopus can synthesize elements from different past solutions, creating new approaches that demonstrate genuine creativity rather than simple repetition of learned behaviors. This innovative capacity suggests that octopus intelligence includes the ability to think analogically, recognizing underlying similarities between superficially different situations. Tool use represents one of the most sophisticated expressions of octopus problem-solving abilities, requiring not only mechanical understanding, but also planning, spatial reasoning, and the ability to recognize potential tools in environmental objects that weren't designed for the purpose they'll serve. When an octopus selects rocks to use as hammers for cracking shells, or chooses coconut shells to use as portable shelters, it demonstrates understanding of physical properties, functional relationships, and the ability to envision how objects might be repurposed to serve specific goals. The planning involved in tool use extends beyond immediate applications to include preparation for future needs. Octopuses have been observed collecting and transporting tools to locations where they anticipate needing them, demonstrating temporal reasoning that involves projecting current understanding into future scenarios. This forward-thinking capability suggests that octopus intelligence includes sophisticated mental modeling that can simulate potential future situations and prepare appropriate responses in advance. Spatial reasoning represents another dimension of octopus problem-solving that reflects the creature's adaptation to the complex, three-dimensional environment of the ocean. When navigating through intricate coral formations or planning routes through underwater mazes, the octopus demonstrates understanding of spatial relationships, geometric principles, and the ability to maintain mental maps of complex environments. This spatial intelligence operates across multiple scales, from the precise manipulation of small objects to the navigation of territories that span hundreds of meters. The octopus's approach to mechanical problems reveals understanding of physical principles that goes beyond simple manipulation to include genuine insight into cause and effect relationships. When working with latches, levers, and other mechanical devices, the creature demonstrates comprehension of how forces are transmitted through mechanical systems, how pressure applied at one point can create effects at distant locations, and how timing and coordination can be crucial to achieving desired outcomes. Sequential problem-solving showcases the octopus's ability to break complex challenges into manageable steps, working through multi-stage solutions with patience and persistence that would be admirable in any intelligent creature. When confronted with puzzles that require several actions to be performed in specific sequence, the octopus can maintain focus on long-term goals while executing intermediate steps, demonstrating working memory and goal management capabilities that rival those of much larger-brained animals. The social dimensions of octopus problem-solving reveal cognitive abilities that extend beyond individual challenges to include understanding of other minds and social dynamics. When competing for resources or territories, octopuses demonstrate strategic thinking that takes into account the likely responses and capabilities of other individuals. This social intelligence involves theory of mind capabilities, the ability to model the mental states and likely behaviors of other creatures that contribute to sophisticated social problem-solving strategies. Flexibility in problem-solving approaches becomes apparent when observing how octopuses adapt their strategies based on changing circumstances or failed attempts. Rather than persisting with ineffective approaches, the creatures demonstrate metacognitive awareness, the ability to monitor their own problem-solving progress and adjust strategies when current approaches aren't working. This cognitive flexibility allows for efficient adaptation to novel challenges and prevents the kind of rigid behavioral patterns that might trap less intelligent creatures in ineffective response cycles. The emotional dimensions of octopus problem-solving add layers of complexity that suggest rich internal lives accompanying the cognitive processes. Different emotional states appear to influence problem-solving strategies, with excited or curious octopuses approaching challenges differently than cautious or stressed individuals. This emotional modulation of cognitive processes suggests that octopus intelligence includes sophisticated integration of reasoning and feeling that may contribute to the creativity and flexibility observed in their problem-solving behaviors. Communication during problem-solving reveals how octopuses can share information about challenges and solutions, suggesting that individual learning can contribute to collective knowledge within octopus communities. When one individual discovers an effective solution to a common problem, this information may be transmitted to other octopuses through observation and imitation, creating opportunities for cultural transmission of problem-solving techniques across generations. The aesthetic dimensions of octopus problem-solving become apparent in situations where creatures have multiple effective solutions available and appear to choose based on criteria that go beyond simple efficiency. Octopuses sometimes select more elaborate or elegant solutions to problems when simpler approaches would work equally well, suggesting that problem-solving serves not only practical functions, but also provides opportunities for creative expression and perhaps even enjoyment of the cognitive challenge itself. Pattern recognition abilities contribute significantly to octopus problem-solving success, as the creatures demonstrate remarkable skill at identifying relevant features in complex environments and recognizing when current situations share important characteristics with previous experiences. This pattern recognition operates across multiple sensory modalities simultaneously, integrating visual, tactile, and chemical information to create comprehensive understanding of environmental situations that can guide appropriate problem-solving responses. The teaching behaviors occasionally observed in octopuses suggest that problem-solving knowledge can be deliberately transmitted from experienced individuals to novices, indicating that the creatures understand not only how to solve problems themselves, but also how to help others develop similar capabilities. This teaching behavior requires sophisticated social intelligence that includes understanding of other minds, recognition of knowledge gaps in others, and the ability to modify one's own behavior to facilitate learning in other individuals. Curiosity-driven problem-solving reveals how octopuses engage with challenges even when there's no immediate survival benefit, suggesting that the creatures find intrinsic value in cognitive challenges and learning experiences. This exploratory problem-solving contributes to the development of general cognitive skills and environmental knowledge that may prove valuable in future survival situations, demonstrating how intelligence can drive behavior that serves long-term adaptive functions rather than immediate needs. The integration of multiple problem-solving strategies within single challenges showcases the sophistication of octopus cognitive architecture as the creatures seamlessly combine mechanical manipulation, spatial reasoning, memory retrieval, social awareness, and creative innovation into coherent approaches to complex problems. This integration happens fluidly and naturally, suggesting that the distributed intelligence system of the octopus has evolved sophisticated coordination mechanisms that allow different cognitive capabilities to work together harmoniously. As you float peacefully in this underwater realm, observing these remarkable demonstrations of creative intelligence, you begin to understand that the octopus's problem-solving abilities represent far more than simple behavioral adaptations. They reveal a form of intelligence that combines logical reasoning with creative innovation, individual learning with social awareness, and practical skills with aesthetic sensibilities, creating a cognitive architecture that approaches challenges with the kind of flexible, creative, and persistent intelligence that we recognize as hallmarks of truly sophisticated minds. The art of problem-solving, as practiced by the octopus, demonstrates that intelligence is not limited to any particular neural architecture or evolutionary lineage, but can emerge wherever life encounters challenges that reward flexible thinking, creative approaches, and the ability to learn from experience. In watching these graceful creatures navigate the cognitive challenges of their underwater world, we glimpse the endless possibilities for intelligence to manifest in forms that both parallel and transcend our own cognitive capabilities, reminding us that the universe of possible minds extends far beyond the boundaries of our own experience and imagination. As you continue floating in this peaceful underwater sanctuary, your awareness expands to encompass one of the most remarkable aspects of octopus cognition: the way these creatures think and navigate in the fluid, three-dimensional space that is their natural home. Unlike terrestrial animals that must contend with gravity and the constraints of surface-bound movement, the octopus experiences intelligence as a liquid phenomenon, flowing freely through all dimensions of its aquatic environment with a grace and spatial sophistication that represents one of evolution's most elegant solutions to the challenges of three-dimensional cognition. The octopus moves through water not simply as a creature traveling from point A to point B, but as an intelligence that inhabits space in ways that fundamentally reshape how we understand the relationship between mind and environment. Every movement is simultaneously an act of navigation, exploration, communication, and thought, with the creature's entire body serving as both vehicle and cognitive instrument for gathering and processing spatial information. The fluid nature of the underwater environment allows for forms of movement and spatial reasoning that would be impossible in terrestrial settings, creating opportunities for intelligence to express itself through the language of three-dimensional flow. Spatial memory in the octopus operates according to principles that reflect the creature's adaptation to an environment where landmarks can shift with currents, where the same location can be approached from countless different angles, and where the third dimension is as navigable and meaningful as the traditional horizontal plane. The octopus maintains detailed mental maps of its territory that include not just the locations of important features, but also information about how these features can be accessed from different directions, at different times of day, and under different environmental conditions. These cognitive maps demonstrate remarkable flexibility and sophistication, incorporating layers of information that go far beyond simple spatial coordinates. The octopus's mental representation of its environment includes temporal information about when different locations are safe or dangerous, chemical information about food sources and territorial boundaries, and dynamic information about how environmental features change with tides, seasons, and the activities of other creatures. This multidimensional mapping system allows the octopus to navigate its territory with efficiency that would be impossible using simpler spatial reasoning strategies. The navigation techniques employed by octopuses reveal cognitive processes that integrate multiple sources of spatial information into coherent understanding of position and direction. Visual landmarks provide one layer of navigational information, but the octopus also uses chemical trails, tactile reference points, magnetic field variations, and even sound patterns to maintain spatial orientation. This multimodal approach to navigation creates redundant information systems that ensure reliable spatial awareness, even when individual navigation cues become unavailable or unreliable. Water column navigation represents a particularly sophisticated aspect of octopus spatial intelligence, as the creature must maintain awareness of its position not just in horizontal space, but also in the vertical dimension that extends from the surface to the seafloor. The octopus can navigate efficiently through complex three-dimensional structures like coral reefs or kelp forests, following pathways that wind up, down, and around obstacles and routes that demonstrate understanding of three-dimensional geometry and spatial optimization principles. The planning of movement routes reveals cognitive processes that consider multiple factors simultaneously, including energy efficiency, safety, resource availability, and social considerations. When traveling between locations in its territory, the octopus doesn't simply follow the most direct path, but rather selects routes that optimize for multiple criteria based on current conditions and anticipated challenges. This route planning demonstrates understanding of trade-offs between different navigational strategies and the ability to make complex decisions that balance multiple competing factors. Current utilization showcases how octopus intelligence can incorporate environmental dynamics into movement strategies, using water movements to enhance efficiency and reduce energy expenditure. The creature demonstrates understanding of how currents flow around obstacles, how thermal layers create different movement opportunities at different depths, and how timing can be used to take advantage of favorable flow conditions. This environmental intelligence allows the octopus to move through its aquatic space with efficiency that approaches optimization principles derived from fluid dynamics. Depth management reveals cognitive abilities that integrate physiological awareness with spatial navigation, as the octopus must monitor and adjust for the effects of pressure changes, light availability, and temperature variations that accompany vertical movement through the water column. The creature's ability to navigate efficiently across different depth zones demonstrates understanding of how environmental conditions change with vertical position and how these changes affect both the octopus's own capabilities and the behavior of other creatures in its environment. Territorial spatial intelligence involves understanding not just the physical features of the octopus's home range, but also the social and temporal dynamics that affect how space can be used. The creature maintains awareness of the territories of neighboring octopuses, the patrol patterns of potential predators, and the seasonal movements of prey species, integrating this social and temporal information into its spatial reasoning to make informed decisions about when and where to travel, hunt, and rest. Hiding place selection demonstrates sophisticated spatial reasoning that considers multiple factors, including concealment effectiveness, escape route availability, proximity to food sources, and construction material accessibility. The octopus evaluates potential den sites using criteria that reflect understanding of three-dimensional space, environmental dynamics, and the spatial behavior patterns of other creatures. This evaluation process involves complex spatial reasoning that integrates immediate sensory information with memory of how similar locations have performed as hiding places in the past. Construction activities reveal how octopus spatial intelligence extends beyond navigation and territory use to include modification and improvement of environmental spaces. When building or modifying dens, the creature demonstrates understanding of structural principles, material properties, and spatial relationships that affect the functionality and effectiveness of constructed spaces. This construction intelligence involves planning that considers not just immediate spatial needs, but also how spatial modifications might affect future use patterns and environmental interactions. Hunting strategies showcase spatial intelligence that operates in real time, as the octopus must predict the movement patterns of prey, plan interception routes, and coordinate multiple arms to execute captures in three-dimensional space. This hunting intelligence involves understanding of physics principles like trajectory prediction, timing calculations, and spatial coordination that allow the octopus to successfully capture prey that may be moving rapidly through complex three-dimensional environments. Escape behaviors demonstrate spatial reasoning that operates under stress, as the octopus must rapidly evaluate multiple escape options and select optimal routes that consider not just immediate safety, but also longer-term strategic considerations. The creature's ability to navigate efficiently towards safety while under threat reveals spatial intelligence that can operate effectively even when cognitive resources are compromised by stress and time pressure. Three-dimensional foraging involves spatial reasoning that considers the vertical distribution of resources, the accessibility of food sources from different approach angles, and the energy costs associated with movement through different parts of the water column. The octopus demonstrates understanding of how resource distribution changes with depth, season, and environmental conditions, allowing for foraging strategies that optimize energy return while minimizing exposure to risk. Camouflage placement reveals spatial intelligence that considers viewing angles, lighting conditions, and the three-dimensional structure of hiding locations. When selecting positions for concealment, the octopus evaluates how its appearance will be perceived from multiple directions, demonstrating understanding of perspective, visual detection principles, and the spatial relationships between its position, potential observers, and environmental features that might aid or hinder concealment. Social spatial intelligence involves understanding how space is used and contested by other octopuses and other species in the marine environment. The creature demonstrates awareness of territorial boundaries, understands the spatial patterns of social interactions, and can predict how its own movement through space might affect social relationships with neighbors and potential mates. This social spatial reasoning requires integration of spatial information with social knowledge and understanding of how space and social relationships interact. Migration and seasonal movement patterns reveal spatial intelligence that operates across larger scales of space and time, as some octopus species demonstrate understanding of how environmental conditions change across their range and how these changes affect resource availability and survival prospects. This large-scale spatial reasoning involves cognitive maps that span dozens or hundreds of kilometers and integrate information about environmental patterns that operate on seasonal or annual timescales. Landmark learning demonstrates how octopus spatial intelligence can adapt to environmental changes, incorporating new spatial information into existing cognitive maps when environmental features appear, disappear, or change their characteristics. This adaptive spatial reasoning allows the octopus to maintain effective navigation capabilities even in dynamic environments where spatial relationships are constantly evolving. Multi-destination trip planning reveals cognitive processes that can optimize routes that include multiple stops, demonstrating understanding of spatial relationships that allows for efficient visiting sequences that minimize total travel distance and time. This trip planning intelligence involves understanding of geometric principles and optimization strategies, that allow the octopus to solve complex spatial logistics problems that would challenge many supposedly more intelligent animals. Spatial problem solving involves using understanding of three-dimensional relationships to solve challenges that require manipulation of objects in space, navigation through complex barriers, or construction of spatial solutions to environmental challenges. The octopus demonstrates ability to visualize spatial transformations, understand how spatial manipulations affect accessibility and functionality, and use spatial reasoning to develop creative solutions to novel spatial challenges. The integration of temporal and spatial information creates four-dimensional navigation capabilities that allow the octopus to understand not just where things are, but when they will be there, enabling prediction of spatial conditions at future times based on understanding of environmental dynamics and movement patterns. This temporal spatial integration represents one of the most sophisticated aspects of octopus liquid intelligence, creating navigation capabilities that operate across both space and time. Water property sensing adds another dimension to octopus spatial intelligence, as the creature can detect and interpret variations in temperature, salinity, chemical composition, and current flow that provide information about spatial location and environmental conditions. This chemical spatial intelligence allows the octopus to navigate using information that is invisible to visual sensors, but provides reliable spatial reference information in aquatic environments. As you float peacefully in this three-dimensional underwater realm, observing how the octopus moves with liquid grace through its spatial environment, you begin to understand that you're witnessing a form of intelligence that has evolved to think in dimensions and according to principles that terrestrial creatures rarely experience. The octopus's liquid intelligence demonstrates how cognitive capabilities can be shaped by environmental opportunities, revealing forms of spatial reasoning and navigation that represent some of evolution's most elegant solutions to the challenges of three-dimensional cognition. The graceful flow of octopus movement through its liquid environment serves as a meditation on the possibilities for intelligence to adapt to and master any environment, revealing how consciousness can learn to inhabit space in ways that transform movement into thought, navigation into creativity, and spatial awareness into a form of liquid poetry that flows through the three-dimensional possibilities of the underwater world with beauty, efficiency, and grace that inspire wonder at the endless adaptability and creativity of intelligent life. As you continue floating in this serene underwater realm, your attention is drawn to one of nature's most sophisticated communication systems, the visual language that flows across the octopus's skin in waves of color and pattern that represent thoughts, emotions, intentions, and social messages expressed through a chromatic vocabulary more complex and nuanced than any human language. This is communication that transcends the limitations of sound and gesture, creating meaning through the direct visualization of internal states and the real-time expression of complex information through living art that transforms the creature's entire body into a dynamic communication interface. The language of color operates according to principles that blur the boundaries between thought and expression, creating a form of communication where mental states become immediately visible and internal processes flow directly onto the creature's surface without the delays and distortions that characterize other forms of communication. When an octopus communicates through its chromatophores, there is no gap between intention and expression, no translation required between thought and signal. The mind speaks directly through the skin in patterns that carry meaning with the immediacy and clarity of pure thought made visible. Each chromatophore represents a single pixel in a biological display system of extraordinary resolution and sophistication, capable of changing color, size, and intensity in fractions of a second in response to neural signals that flow directly from the octopus's central nervous system and distributed arm intelligence networks. The coordination of millions of these cellular displays creates communication capabilities that operate with bandwidth and complexity that far exceed any technological communication system humans have yet developed, allowing for the simultaneous transmission of multiple types of information through different aspects of the visual display. Basic emotional states find expression through fundamental color patterns that appear to be universal across octopus species, creating a foundational vocabulary of chromatic communication that expresses primary affective states with clarity and consistency. Calm contentment typically manifests as gentle, flowing patterns of muted colors, soft browns, pale yellows, and gentle waves of lighter and darker tones that ripple slowly across the creature's surface like visual representations of peaceful breathing. These tranquil displays create an atmosphere of relaxation and safety that can be perceived by other octopuses and even by observant members of other species. Excitement and arousal produce more dynamic and intense chromatic displays, with brighter colors appearing in rapid succession and patterns that move more quickly across the skin surface. Reds, oranges, and yellows often dominate these excited displays, creating visual representations of heightened energy and emotional intensity that communicate the octopus's current state of activation to potential mates, competitors, or observers. The speed and intensity of these pattern changes seem to correlate directly with the level of arousal, creating a visual readout of internal excitement that provides precise information about the creature's emotional state. Defensive communications utilize specific color combinations and patterns that serve both as warnings to potential threats and as signals to other octopuses about the presence of danger. These defensive displays often involve rapid alternation between contrasting colors, creating flickering or strobing effects that draw attention while conveying urgency and potential threat. The stark black and white patterns that often characterize defensive displays provide maximum visual contrast that ensures the warning message will be clearly visible even under challenging lighting conditions or when viewed from substantial distances. Territorial assertions through chromatic communication involve displays that combine size enhancement through raised papillae with bold color patterns that communicate ownership and determination to defend important resources. These territorial displays often involve specific geometric patterns, stripes, spots, and angular designs that may serve as visual signatures identifying individual octopuses while simultaneously communicating their claim to particular areas or resources. The persistence and intensity of these displays provide information about the strength of the territorial claim and the likelihood that the displaying individual will engage in actual physical defense if challenged. Courtship communications represent some of the most elaborate and sophisticated expressions in the octopus chromatic vocabulary, involving complex sequences of patterns that unfold over extended periods and incorporate multiple layers of visual information. Male octopuses often display intricate patterns that combine flowing waves of color with geometric designs, rhythmic pulsations, and synchronized movements that create multimedia courtship performances of remarkable beauty and complexity. These courtship displays appear to communicate not just reproductive intentions, but also information about the male's health, genetic quality, and suitability as a mate. Hunting communications involve more subtle chromatic expressions that coordinate hunting activities between different arms while maintaining concealment from potential prey. These hunting patterns often involve localized color changes that don't extend across the entire body surface, allowing different parts of the octopus to communicate with each other while maintaining overall camouflage effectiveness. The coordination required for these selective chromatic communications demonstrates sophisticated control over the visual display system that allows for multiple simultaneous communication channels operating independently on different parts of the body surface. Social recognition patterns suggest that individual octopuses may have characteristic chromatic signatures that serve as visual identification markers, allowing for individual recognition within octopus communities. These signature patterns might include specific color combinations, preferred geometric arrangements, or characteristic timing patterns in chromatic displays that function like visual names or identities. The ability to maintain and recognize these individual chromatic signatures would support more complex social relationships than would be possible with purely anonymous interactions. Threat assessment communications involve chromatic displays that provide information about the nature and severity of detected threats, allowing octopuses to coordinate appropriate responses without the delays that would be associated with other forms of communication. Different types of threats appear to elicit different characteristic color patterns, creating a threat classification system that can rapidly communicate whether danger comes from above or below, whether it involves a familiar or unfamiliar threat type, and whether immediate flight or defensive positioning is the most appropriate response. Learning and memory are expressed through chromatic communications as octopuses display patterns that appear to reflect memory retrieval and learning processes. When encountering familiar situations or objects, octopuses often display specific color patterns that may represent the activation of relevant memories and the integration of past experience with current sensory input. These memory-related displays provide external evidence of internal cognitive processes and suggest that chromatic communication serves not just social functions, but also cognitive support functions that aid in memory consolidation and retrieval. Pain and distress communications utilize specific chromatic patterns that alert other octopuses to injury or illness, potentially eliciting helping behaviors or at least warning others about potential sources of danger in the environment. These distress displays often involve color patterns that are distinctly different from normal behavioral displays, ensuring that the distress communication will be recognized as indicating unusual and potentially dangerous conditions that require attention and appropriate response. Play and exploration behaviors are accompanied by chromatic displays that appear to express curiosity, engagement, and the positive effect associated with learning and environmental investigation. These exploratory displays often involve gentle, flowing patterns that suggest openness and receptivity to new information, creating visual representations of the cognitive states that support effective learning and environmental adaptation. The presence of these play-related chromatic patterns suggests that octopuses experience positive emotions associated with learning and exploration. Environmental information sharing through chromatic communication allows octopuses to transmit information about local conditions, resource availability, and environmental changes to other members of their species. These informational displays might include patterns that indicate the location of food sources, the presence of suitable nesting materials, or changes in local environmental conditions that affect survival and reproduction. This environmental information sharing supports community awareness and coordinated responses to environmental challenges. Deception and misdirection represent sophisticated applications of chromatic communication that involve deliberate manipulation of visual signals to create false impressions in observers. Octopuses can display patterns that suggest false emotional states, fake injuries that redirect predator attention, or camouflage patterns that make them appear to be different species entirely. This deceptive use of chromatic communication requires understanding of how visual signals will be interpreted by different types of observers and the ability to manipulate these interpretations strategically. Rhythmic and temporal patterns in chromatic communication create opportunities for complex information encoding that utilizes timing and sequence, as well as color and spatial arrangement to convey meaning. These temporal patterns might involve synchronized flashing between different body regions, rhythmic alternation between different color combinations, or sequential activation of different chromatic displays that unfold over extended time periods. The timing patterns add temporal dimensions to the spatial complexity of chromatic communication, creating opportunities for encoding information that transcends simple static visual displays. Cultural transmission of chromatic communication patterns may occur through observational learning, with young octopuses acquiring chromatic vocabulary by observing the displays of adult community members. This cultural transmission could lead to regional dialects in chromatic communication, with different octopus populations developing slightly different conventions for expressing similar concepts through their visual displays. The possibility of cultural evolution in chromatic communication adds another layer of complexity to octopus social organization and community structure. Emotional contagion through chromatic displays allows emotional states to spread rapidly through octopus communities, with the chromatic expressions of one individual influencing the emotional states and corresponding displays of nearby octopuses. This emotional contagion supports coordinated community responses to threats, opportunities, and environmental changes, creating collective emotional states that enhance group survival and effectiveness. The visual nature of this emotional transmission makes it particularly rapid and effective in aquatic environments where other forms of communication might be less reliable. Environmental responsiveness in chromatic communication involves displays that reflect and respond to environmental conditions, with color patterns that adapt to lighting conditions, background environments, and seasonal changes. These environmentally responsive displays ensure that chromatic communications remain effective across varying environmental conditions while providing additional information about the communicator's current environmental context. This environmental integration demonstrates how Octopus communication systems are designed to work effectively within the dynamic underwater environment. Learning and adaptation in chromatic communication involve the continuous refinement and development of visual display capabilities throughout the octopus's lifetime, with communication skills becoming more sophisticated and effective through experience and practice. Young octopuses gradually develop more complex and nuanced chromatic vocabularies, while adults continue to refine and adapt their communication strategies based on social feedback and environmental changes. This lifelong development of communication abilities suggests that chromatic language represents a learned skill rather than purely instinctive behavior. The integration of chromatic communication with other sensory modalities creates multimodal communication systems that combine visual displays with chemical signals, tactile interactions, and behavioral cues to create rich, complex messages that convey information through multiple channels simultaneously. This multimodal integration ensures communication effectiveness even when individual sensory channels are compromised by environmental conditions, while providing opportunities for encoding additional layers of meaning through the coordination of different communication modalities. As you float peacefully in this underwater realm, observing the flowing patterns of chromatic communication that transform the octopus's skin into a living canvas of expression, you begin to understand that you're witnessing one of evolution's most remarkable achievements in communication technology. The language of color represents a form of communication that transcends the limitations of sequential, symbolic language, creating instead a medium where meaning flows directly from mind to mind through the immediate expression of thought and feeling in patterns of living light. This chromatic language demonstrates possibilities for communication that extend far beyond human linguistic capabilities, revealing how intelligence can develop communication systems that operate according to principles of direct neural expression rather than symbolic representation. In the flowing patterns of color that dance across the octopus's skin, we glimpse possibilities for meaning and expression that remind us how many different forms communication can take when intelligence is free to explore the full spectrum of possibilities for sharing information, emotion, and intention with others of its kind. As you continue your peaceful observation in this underwater sanctuary, floating weightlessly among the gentle currents and filtered sunlight, you witness one of the most remarkable demonstrations of intelligence in the natural world. The octopus's sophisticated use of tools and environmental manipulation that reveals cognitive abilities once thought to be unique to humans and a few other highly intelligent species. But here, in the depths of the ocean, intelligence manifests through tentacles that can transform ordinary objects into specialized instruments, demonstrating planning, foresight, and creative problem-solving that challenges our understanding of how minds can interact with and reshape their physical environment. The octopus's approach to tool use begins with a form of environmental awareness that recognizes potential utility in objects that other creatures might ignore or consider merely decorative elements of the underwater landscape. A discarded coconut shell becomes a portable shelter. A collection of rocks transforms into construction materials for architectural projects, and pieces of broken coral evolve into precision instruments for extracting food from tight spaces. This recognition of hidden potential in environmental objects demonstrates cognitive abilities that extend far beyond simple pattern recognition to include genuine understanding of functional relationships and creative visualization of alternative uses. Watching an octopus select tools reveals decision-making processes that integrate multiple factors, including immediate needs, anticipated future requirements, material properties, and environmental constraints. The creature doesn't simply grab the nearest available object, but rather evaluates different options based on criteria that include size, weight, durability, and functional suitability for intended purposes. This evaluation process demonstrates understanding of physical properties and mechanical principles that allows the octopus to predict how different objects will perform in various applications. The collection and transport of tools showcases planning abilities that extend across both time and space, as octopuses gather useful objects and carry them to locations where they anticipate needing them for future activities. This forward-thinking behavior requires cognitive abilities that include memory of past tool use experiences, understanding of recurring functional needs, and the ability to project current environmental knowledge into future scenarios. The effort invested in tool collection and transport demonstrates that octopuses understand the value of preparation and can make behavioral investments that will pay dividends in future situations. Shell selection for portable shelters represents one of the most sophisticated examples of octopus tool use, involving evaluation criteria that include not just immediate protection needs, but also considerations of mobility, concealment effectiveness, and compatibility with the octopus's size and behavioral requirements. The creature must assess how different shells will affect its movement capabilities, how well they will provide concealment in different environments, and how they might be combined with other materials to create more effective shelter systems. This shell selection process demonstrates understanding of trade-offs between different functional requirements and the ability to optimize tool choice based on complex, multi-criteria decision-making. Rock manipulation for construction purposes reveals mechanical understanding that includes principles of leverage, balance, stability, and architectural design that allow octopuses to create structures that enhance their survival prospects and environmental control. When building defensive barriers or modifying den sites, the octopus demonstrates understanding of how different rock arrangements will affect structural integrity, defensive effectiveness, and aesthetic appeal. This construction intelligence involves spatial reasoning, engineering principles, and creative problem-solving that results in architectural achievements that are both functional and aesthetically pleasing. Precision tool use for food extraction showcases the octopus's ability to employ delicate manipulation techniques that require fine motor control, spatial reasoning, and understanding of mechanical advantage principles. When using thin pieces of coral or shell to extract prey from cracks and crevices, the octopus demonstrates hand-eye coordination that rivals that of any primate, combined with understanding of leverage and mechanical force transmission that allows for efficient food extraction with minimal energy expenditure. This precision tool use requires integration of sensory feedback, motor control, and mechanical understanding that represents sophisticated sensor-motor intelligence. Multi-tool coordination involves the simultaneous use of multiple tools by different arms to accomplish complex tasks that require parallel processing and coordination between independent manipulation systems. An octopus might use one arm to stabilize a shell, while another arm positions a rock tool, and a third arm manipulates the target object, creating coordinated tool use that requires sophisticated temporal and spatial coordination between multiple semi-independent cognitive systems. This multi-tool coordination demonstrates the advantages of distributed intelligence for complex manipulation tasks that exceed the capabilities of single-tool systems. Tool modification behaviors reveal cognitive abilities that include understanding of how material properties can be altered to improve functional effectiveness for specific applications. Octopuses have been observed breaking rocks to create tools of appropriate size, scraping shells to improve their fit or functionality, and combining different materials to create composite tools that incorporate the advantageous properties of multiple components. This tool modification demonstrates creative problem-solving that goes beyond simple object selection to include active material engineering that optimizes tool performance for specific tasks. Environmental engineering through tool use involves large-scale environmental modifications that require planning, resource management, an understanding of how changes to environmental structure will affect future behavioral options and survival prospects. When octopuses use tools to modify their territories, creating barriers, improving shelter sites, or establishing food storage areas, they demonstrate understanding of how environmental modifications affect long-term habitat quality and resource availability. This environmental engineering represents sophisticated interaction between cognitive planning and physical environmental manipulation. Tool sharing and social aspects of tool use reveal cooperative behaviors and social learning mechanisms that allow octopuses to benefit from the tool use innovations of other community members. Observations of tool use techniques being transmitted between individuals suggest that octopuses can learn from watching others, developing cultural traditions of tool use that may vary between different populations and geographic regions. This social dimension of tool use adds complexity to octopus intelligence that includes understanding of social learning opportunities and the ability to integrate observed techniques into personal behavioral repertoires. Seasonal tool use patterns demonstrate temporal intelligence that includes understanding of how environmental changes affect tool requirements and availability throughout annual cycles. Octopuses may collect and store certain types of tools during seasons when they are abundant, anticipating future needs that will arise when environmental conditions change. This seasonal planning requires memory of annual cycles, understanding of cause and effect relationships between environmental conditions and tool availability, and the ability to make behavioral investments based on anticipated future needs. Creative tool innovations involve the development of novel tool use techniques that go beyond learned or instinctive behaviors to include genuine creativity and innovation in problem-solving approaches. Individual octopuses have been observed developing unique tool use strategies that appear to be personal innovations rather than learned behaviors, suggesting that octopus intelligence includes creative problem-solving capabilities that can generate new solutions to environmental challenges. These innovations may then be observed and learned by other octopuses, contributing to the cultural evolution of tool use techniques within octopus communities. Tool use for non-survival purposes reveals cognitive motivations that extend beyond immediate survival needs to include play, exploration, and perhaps aesthetic expression through environmental manipulation. Octopuses sometimes engage in tool use behaviors that appear to serve no obvious survival function, suggesting that these activities may provide cognitive stimulation, practice opportunities for skill development, or simply intrinsic satisfaction from successful manipulation of environmental objects. This non-utilitarian tool use suggests that octopus intelligence includes intrinsic motivation for interaction with environmental objects that goes beyond simple survival requirements. Problem-solving with tools involves using objects to overcome environmental challenges that cannot be addressed through direct physical manipulation alone. When confronted with obstacles that block access to food or shelter, octopuses can use tools to extend their reach, modify environmental barriers, or create mechanical advantage that allows them to accomplish goals that would otherwise be impossible. This tool-mediated problem-solving demonstrates understanding of how tools can extend cognitive and physical capabilities while revealing flexible thinking that can adapt tool use strategies to novel challenges. Memory and learning in tool use involve the accumulation of knowledge about tool effectiveness, environmental object properties, and manipulation techniques that improves performance and efficiency over time. Octopuses remember which types of tools work best for different tasks, where useful objects can be found in their environment, and how to optimize manipulation techniques for maximum effectiveness. This learning creates expertise in tool use that represents accumulated intelligence about environmental interaction and manipulation strategies. Aesthetic dimensions of tool use become apparent when octopuses make choices about environmental modification and object selection that appear to be influenced by aesthetic criteria rather than purely functional considerations. When arranging objects around den sites or selecting materials for construction projects, octopuses sometimes appear to make choices based on visual appeal, symmetry, or other aesthetic factors that suggest that tool use serves not just functional purposes, but also provides opportunities for creative expression and environmental beautification. Teaching and demonstration of tool use techniques reveals social intelligence that includes understanding of how knowledge can be transmitted to other individuals through behavioral demonstration and guided practice. Adult octopuses have been observed demonstrating tool use techniques to younger individuals in ways that appear to be deliberate teaching behaviors rather than simple coincidental observation opportunities. This teaching behavior requires sophisticated social intelligence that includes understanding of other minds, recognition of knowledge gaps in others, and the ability to modify one's own behavior to facilitate learning in other individuals. The integration of tool use with other cognitive capabilities creates synergistic effects that enhance overall problem-solving effectiveness and environmental control beyond what would be possible through either tool use or other cognitive abilities alone. When octopuses combine tool use with their camouflage abilities, spatial intelligence, and social awareness, they create comprehensive strategies for environmental interaction that demonstrate how different aspects of intelligence can work together to create capabilities that exceed the sum of their individual components. Conservation and maintenance of tools reveal understanding of tool value and the importance of preserving useful objects for future applications. Octopuses often maintain collections of useful tools, storing them in accessible locations and protecting them from damage or appropriation by other creatures. This tool conservation behavior requires understanding of future value, memory of tool locations, and the motivation to invest energy in maintenance activities that provide no immediate benefit but enhance future capabilities. Environmental impact awareness in tool use involves understanding of how tool use activities affect environmental conditions and the behavior of other creatures in the local ecosystem. Octopuses appear to be aware of how their construction and modification activities affect local environmental conditions and may modify their tool use strategies to minimize negative impacts on their environment or to enhance conditions for other beneficial species. This environmental awareness demonstrates sophisticated understanding of ecological relationships and the long-term consequences of environmental modification activities. As you float peacefully in this underwater realm, observing these remarkable demonstrations of tool use intelligence, you begin to understand that the octopus's manipulation of environmental objects represents far more than simple instrumental behavior. The tools of the deep reveal cognitive capabilities that include creative problem-solving, forward planning, aesthetic sensibility, social learning, and environmental engineering that transform the octopus from a passive inhabitant of its underwater world into an active architect and engineer that reshapes its environment to better serve its needs and preferences. The gentle precision with which the octopus manipulates its tools, the thoughtful selection of materials for different purposes, and the creative integration of multiple objects into complex functional systems demonstrate that intelligence can manifest through tentacles and suckers just as effectively as through hands and fingers, revealing how consciousness can extend itself into the physical world through tools that become extensions of the mind, allowing intelligence to reshape reality according to its own creative vision and practical requirements. Beneath the surface of what might appear to be solitary existence, the octopus reveals layers of social complexity that challenge our assumptions about intelligence, community, and the subtle ways that highly intelligent creatures can maintain meaningful relationships while preserving the independence that characterizes their species. The social world of the octopus operates according to principles that emphasize quality over quantity, depth over breadth, and sophisticated communication over simple gregariousness, creating forms of social intelligence that may be more nuanced and meaningful than the more obvious social behaviors exhibited by creatures that live in large, visible groups. The territorial nature of octopus social organization creates opportunities for complex social relationships that develop through repeated interactions between neighboring individuals who share adjacent territories and encounter each other regularly during foraging, exploration, and territorial maintenance activities. These neighborhood relationships often involve sophisticated recognition systems that allow individual octopuses to identify and remember specific neighbors, developing personalized interaction patterns that reflect the unique characteristics and behavioral tendencies of each individual in the local community. Recognition of individual neighbors involves sophisticated cognitive processes that integrate visual appearance, behavioral patterns, territorial preferences, and social interaction history into comprehensive individual profiles that allow for personalized social responses. An octopus can distinguish between a familiar neighbor who typically engages in peaceful interactions and an unfamiliar intruder who might represent a territorial threat, adjusting its social behaviors appropriately based on individual recognition and past interaction experiences. This individual recognition capability supports the development of stable social relationships that persist over extended periods and contribute to community stability. Boundary negotiations between territorial neighbors demonstrate social intelligence that includes understanding of property rights, conflict resolution, and the benefits of cooperative arrangements that reduce energy expenditure on territorial defense while maintaining access to necessary resources. Rather than engaging in constant aggressive encounters, neighboring octopuses often develop mutually acceptable territorial arrangements that involve shared boundaries, temporal sharing of overlapping areas, and cooperative monitoring of territorial integrity against intrusion by unfamiliar individuals. Communication protocols for social interactions involve sophisticated integration of chromatic displays, behavioral signals, and spatial positioning that convey complex social information about intentions, emotional states, and social relationships. The social communication system allows octopuses to express subtle gradations of social intent, from friendly curiosity to cautious interest to firm territorial assertion, creating opportunities for fine-tuned social interactions that can be calibrated to match the specific social context and the nature of the relationship between the interacting individuals. Cooperative behaviors emerge in situations where individual octopuses can benefit from coordinated activities that achieve goals more efficiently than purely independent efforts would allow. While octopuses are primarily solitary creatures, they can engage in temporary cooperative arrangements that involve shared hunting activities, coordinated territorial defense, or mutual assistance during environmental challenges. These cooperative behaviors require social intelligence that includes understanding of mutual benefit, temporal coordination, and the ability to maintain cooperative relationships despite the strong independence drive that characterizes the species. Conflict resolution strategies reveal social intelligence that emphasizes de-escalation, avoidance of costly physical confrontations, and the development of social arrangements that allow competing individuals to coexist without constant aggressive interactions. Octopuses have developed sophisticated ritualized threat displays that allow for the communication of competitive intent without the risks associated with actual physical combat, creating opportunities for social dominance to be established and maintained through communication rather than through dangerous physical encounters. Mating social behaviors involve some of the most complex social interactions in the octopus behavioral repertoire, requiring sophisticated coordination between individuals who must overcome their natural territorial instincts to engage in reproductive activities that are essential for species continuation. The courtship process involves elaborate social negotiations that include individual recognition, compatibility assessment, and the establishment of temporary social bonds that allow for successful reproductive activities while maintaining the safety and autonomy of both participants. Parental social behaviors, particularly in species where parental care extends beyond simple egg laying, reveals social intelligence that includes understanding of offspring needs, protection strategies, and the development of parent-offspring relationships that support successful development and transition to independence. The social bonds between parents and offspring involve recognition systems, communication protocols, and behavioral coordination that demonstrate sophisticated understanding of social relationships and developmental needs. Social learning opportunities arise when octopuses observe the behaviors of other individuals and incorporate observed techniques, strategies, or solutions into their own behavioral repertoires. This observational learning capability supports the cultural transmission of useful techniques and innovations throughout octopus communities, creating opportunities for collective knowledge accumulation that enhances the survival prospects and environmental adaptability of entire populations. Information sharing between community members involves communication about environmental conditions, resource availability, threat presence, and other information that can benefit multiple individuals in a local social network. This information sharing may occur through direct communication during social encounters, or through indirect communication that involves leaving chemical or visual signals that can be detected and interpreted by other community members who encounter these environmental markers during their own activities. Social hierarchy and dominance relationships in octopus communities involve subtle social arrangements that minimize direct confrontation while establishing social structures that reduce conflict and facilitate resource sharing arrangements. These social hierarchies are typically based on factors including size, age, territorial quality, and individual behavioral characteristics, and are maintained through communication and behavioral displays rather than through constant aggressive interactions. Mentoring relationships between experienced adults and younger community members provide opportunities for knowledge transfer and skill development that enhance the survival prospects and environmental competence of developing individuals. These mentoring relationships may involve demonstration of effective techniques, sharing of territorial knowledge, and protection of young individuals during vulnerable developmental periods when they are learning to navigate the social and environmental challenges of adult life. Alliance formation between individuals who share common interests or face similar challenges creates opportunities for cooperative problem solving and mutual support that enhances the effectiveness of individual efforts while maintaining the independence that characterizes octopus social organization. These alliances may be temporary arrangements that address specific challenges or longer-term relationships that provide ongoing mutual benefits to the participating individuals. Social memory systems allow octopuses to maintain detailed records of past social interactions, individual relationship histories, and community social dynamics that inform current social decision-making and relationship management strategies. This social memory capability enables the development of sophisticated social strategies that take into account the long-term consequences of social behaviors and the importance of maintaining positive relationships with community members who may be encountered repeatedly over extended periods. Cultural variation between different octopus populations reveals how social learning and information transmission can lead to the development of regional differences in social behaviors, communication conventions, and community organization patterns. These cultural differences demonstrate that octopus social intelligence includes the flexibility to adapt social strategies to local environmental conditions and social contexts, while maintaining the fundamental social capabilities that characterize the species. Social stress management involves behavioral and physiological adaptations that allow octopuses to maintain social relationships while managing the stress that can result from social interactions and community living. These stress management strategies include behavioral techniques for avoiding excessive social stimulation, physiological adaptations that moderate stress responses during social encounters, and social skills that minimize conflict and promote positive social interactions. Empathy and emotional recognition in octopus social interactions suggest that these creatures possess sophisticated understanding of the emotional states and needs of other individuals, allowing for social responses that are calibrated to the emotional context of social situations. This emotional intelligence supports the development of meaningful social relationships and enhances the effectiveness of social communication by ensuring that social behaviors are appropriate to the emotional needs and states of other community members. Social play behaviors reveal that octopus social interactions serve not only survival and reproductive functions, but also provide opportunities for enjoyment, skill development, and social bonding that contribute to individual well-being and community cohesion. These play behaviors demonstrate that octopus social intelligence includes understanding of the intrinsic value of positive social interactions and the importance of maintaining social connections that enhance quality of life beyond simple survival requirements. Community defense strategies involve coordinated responses to threats that affect multiple community members, demonstrating social intelligence that includes understanding of collective interests and the ability to organize cooperative responses to challenges that exceed the capabilities of individual defensive efforts. These community defense behaviors require sophisticated social coordination and communication that allows for rapid mobilization of collective resources in response to environmental threats. Social innovation and creativity in Octopus communities involve the development of novel social behaviors, communication techniques, and community organization strategies that enhance social effectiveness and adaptability. Individual octopuses can develop social innovations that are then observed and adopted by other community members, contributing to the cultural evolution of social practices that enhance community functioning and individual social success. Conflict mediation behaviors suggest that some octopuses may serve social roles that involve intervention in conflicts between other community members, helping to resolve social disputes and maintain community harmony. These mediation behaviors require sophisticated social intelligence that includes understanding of conflict dynamics, communication skills that can influence the behavior of other individuals, and social motivation to invest energy in community welfare beyond immediate personal interests. Social network maintenance involves ongoing efforts to sustain and strengthen social relationships through regular interaction, mutual support, and shared activities that reinforce social bonds and maintain community coherence. This network maintenance requires social intelligence that includes understanding of relationship dynamics, recognition of the importance of social investment, and the ability to balance individual needs with social responsibilities and opportunities. The depth and sophistication of octopus social intelligence challenges our assumptions about what form social life can take among highly intelligent creatures, revealing that meaningful social relationships and complex community dynamics can emerge even among species that value independence and solitude. The social secrets of the octopus demonstrate that intelligence can create social solutions that emphasize quality over quantity, depth over breadth, and meaningful connection over superficial gregariousness, showing how consciousness can find ways to maintain essential social bonds while preserving the autonomy and independence that allow for individual creativity and self-expression. In the subtle social dances that unfold between octopus neighbors, in the complex negotiations that characterize territorial relationships, and in the sophisticated communication that allows for conflict resolution and cooperative arrangements, we discover that social intelligence can manifest in forms that are both different from and similar to our own social capabilities, reminding us that the possibilities for social organization and community life are as diverse and creative as intelligence itself. In the quiet hours when the ocean's activity subsides and the underwater world settles into its own version of nighttime rest, the octopus reveals perhaps its most mysterious and intriguing cognitive behavior, sleep patterns and neural activity that suggest these remarkable creatures may experience something analogous to dreams, opening windows into forms of consciousness that challenge our understanding of what it means to have an inner life, to process experiences during rest, and to maintain the kind of rich mental activity that we associate with the most sophisticated forms of awareness. The discovery of sleep-like states in octopuses represents one of the most significant recent advances in understanding cephalopod consciousness, revealing that these invertebrate minds engage in patterns of rest and activity that bear striking resemblances to the sleep cycles that characterize vertebrate consciousness. During these quiet periods, the octopus's behavior changes dramatically from the active, exploratory patterns of waking life to a more passive, internally focused state where external responsiveness decreases while internal neural activity follows patterns that suggest complex information processing is occurring even during apparent rest. The physical manifestations of octopus sleep include changes in body posture, breathing patterns, and chromatic displays that create visual evidence of altered consciousness states. A sleeping octopus often adopts specific resting positions that minimize energy expenditure while maintaining some level of environmental awareness. typically selecting protected locations that provide security from predators while allowing for rapid awakening if threats arise. The creature's arms may arrange themselves in characteristic patterns that differ from waking postures, creating visual indicators that consciousness has shifted into a different operational mode. Chromatic displays during sleep provide the most fascinating evidence for dreamlike states in octopuses, as the creature's skin continues to show waves of color and pattern changes even when the animal appears to be completely unconscious. These sleep-related color patterns differ qualitatively from waking chromatic displays, often involving flowing, abstract patterns that seem to reflect internal neural activity rather than external environmental stimuli or social communication needs. The colors may shift through sequences that appear random to external observers, but may represent the visual manifestation of memory consolidation, emotional processing, or other internal cognitive activities. Memory consolidation during sleep appears to play a crucial role in octopus learning and cognitive development, with sleep periods providing opportunities for the integration of new experiences with existing knowledge, the strengthening of important memories, and the organization of information in ways that enhance future learning and problem-solving capabilities. The distributed nature of octopus intelligence, with significant neural processing occurring in the arms, as well as the central brain, may create particularly complex memory consolidation processes that involve coordination between multiple semi-independent neural networks. Emotional processing during sleep may provide opportunities for octopuses to integrate the emotional aspects of their experiences, processing social interactions, environmental challenges, and other emotionally significant events in ways that contribute to emotional regulation and psychological health. The chromatic displays that occur during sleep sometimes suggest emotional content, with color patterns that resemble those associated with specific emotional states during waking hours, suggesting that emotional experiences continue to be processed and integrated during rest periods. REM-like sleep phases in octopuses involve periods of increased neural activity accompanied by distinctive behavioral and physiological changes that parallel the rapid eye movement sleep that characterizes dreaming states in mammals. During these active sleep phases, the octopus may show increased chromatic activity, subtle movements of arms and body, and changes in breathing patterns that suggest heightened internal activity despite continued unconsciousness. These REM-like phases may represent periods when the most complex cognitive processing occurs during sleep. Learning enhancement through sleep appears to be a significant function of octopus rest periods, with evidence suggesting that problem-solving abilities and memory performance improve following sleep periods that allow for the consolidation and organization of recently acquired information. This sleep-dependent learning enhancement may be particularly important for octopuses given their relatively short lifespans and the need to acquire complex survival skills quickly and efficiently during their limited developmental periods. Neural replay during sleep may involve the reactivation of neural patterns that were established during waking experiences, allowing for the rehearsal and strengthening of behavioral sequences, spatial memories, and problem-solving strategies. This neural replay could contribute to skill development, memory consolidation, and the integration of new learning with existing knowledge in ways that enhance overall cognitive performance and adaptive capabilities. Individual differences in sleep patterns suggest that octopus sleep behavior varies between individuals in ways that may reflect personality differences, developmental stages, or environmental adaptations. Some octopuses may require more sleep than others, show different patterns of chromatic activity during rest, or demonstrate varying levels of environmental responsiveness during sleep periods. These individual differences in sleep behavior provide additional evidence for the complexity and individuality of octopus consciousness. Environmental influences on sleep include factors such as light cycles, temperature changes, predator activity patterns, and social dynamics that affect when and how octopuses enter sleep states. The ability to adapt sleep patterns to environmental conditions demonstrates flexibility in consciousness states that allows octopuses to optimize rest periods while maintaining appropriate levels of vigilance and environmental responsiveness based on current conditions and threat levels. In the gentle currents of this underwater realm, where you have journeyed through the remarkable landscape of octopus intelligence, you discover that the wisdom flowing through 8 arms represents far more than an exotic curiosity or an interesting biological adaptation. The distributed consciousness of the octopus reveals fundamental truths about the nature of intelligence itself, demonstrating that awareness, creativity, and wisdom can emerge through neural architectures that operate according to principles completely different from our own centralized cognitive systems. The octopus mind teaches us that intelligence is not a single phenomenon, but rather a family of related capabilities that can manifest through countless different organizational strategies. Where human intelligence flows through hierarchical networks that channel information towards centralized processing centers, octopus intelligence operates through distributed networks that process information in parallel across multiple semi-independent systems. This distributed approach creates cognitive capabilities that are both remarkably similar to and fundamentally different from our own mental processes. The lessons of octopus intelligence extend far beyond the boundaries of marine biology to offer insights into the fundamental nature of consciousness, creativity, and the endless possibilities for how minds can organize themselves to meet the challenges of existence. In watching how 8 arms coordinate their activities while maintaining individual autonomy, we glimpse possibilities for cooperation and integration that respect individual capabilities while achieving collective goals that exceed what any single component could accomplish alone. The patience and persistence that characterize octopus problem-solving reveal wisdom about how intelligence can approach challenges with the kind of methodical, thoughtful persistence that allows for creative solutions to emerge through careful exploration rather than rushed decision-making. The octopus demonstrates that effective intelligence often involves the willingness to explore problems thoroughly, to try multiple approaches, and to integrate information from many sources before committing to particular solutions. The integration of thinking and feeling that characterizes octopus cognition offers insights into forms of intelligence that seamlessly blend rational analysis with emotional wisdom, creating decision-making processes that consider not just logical factors, but also the emotional and aesthetic dimensions of choices. The octopus's thinking skin makes visible the emotional aspects of cognitive processing, revealing how feeling and thinking can be integrated into unified approaches to understanding and responding to environmental challenges. The creative flexibility that flows through the octopus's distributed intelligence demonstrates how consciousness can remain adaptable and innovative even while operating according to consistent principles and maintaining stable identity. The octopus shows us that intelligence can be both reliable and creative, both systematic and innovative, both consistent and adaptable, revealing possibilities for cognitive organization that transcend traditional distinctions between structure and flexibility. The environmental integration that characterizes octopus intelligence reveals wisdom about how minds can develop intimate relationships with their surroundings, becoming so attuned to environmental patterns and possibilities that the boundaries between self and environment become permeable and mutually enriching. The octopus teaches us that intelligence can enhance not just individual capabilities, but also environmental relationships that create mutual benefits for both mind and world. The social wisdom of the octopus demonstrates how intelligence can maintain meaningful relationships while preserving individual autonomy, creating forms of community that emphasize quality over quantity and depth over breadth. The octopus shows us that social intelligence can manifest through subtle, respectful interactions that honor individual differences while creating opportunities for mutual support and shared wisdom. In the flowing movements of 8 arms, in the thinking patterns that dance across chromatophore-covered skin, in a liquid grace of 3-dimensional navigation, and the creative problem-solving that transforms environmental challenges into opportunities for growth and learning, the octopus reveals that intelligence is far more diverse, creative, and beautiful than we ever imagined. These creatures of the deep show us that consciousness can flow through tentacles just as effectively as through neurons, that wisdom can emerge from distributed processing just as readily as from centralized control, and that the universe of possible minds extends infinitely beyond the boundaries of our own cognitive experience. The octopus mind reminds us that intelligence is not a scarce resource hoarded by a few fortunate species, but rather a fundamental property of life that can emerge wherever the challenges of existence create opportunities for learning, adaptation, and creative response. In the gentle embrace of the ocean depths, surrounded by creatures whose intelligence flows through 8 arms and expresses itself through living art, we discover that consciousness is far more abundant, diverse, and wonderful than we ever dared to dream. Rest now in the knowledge that intelligence takes countless forms throughout the living world, that consciousness flows through neural networks as diverse as the creatures that contain them, and that wisdom can emerge from any system capable of learning, adapting, and creating responses to the beautiful challenges of existence. Let the gentle wisdom of 8 arms guide you into peaceful sleep, knowing that tomorrow will bring new opportunities to appreciate the endless creativity and remarkable diversity of the intelligent life that shares our world, reminding us always that the universe of minds is vast, wonderful, and filled with forms of consciousness that continue to surprise, delight, and inspire us with their beauty, complexity, and grace.